We're gonna go over a level 4 problem regarding forces. Um, Problem 15, the one that you see on my screen, stems from your forces review worksheet. So this is how it goes. Given three forces F1, F2, F3, whose magnitudes are respectively 100 newtons, 40, and 6 newtons, determine the vector diagram, the net force, stating whether it is balanced or not, and what will happen to the object under the action of the forces. And finally, you should determine the net acceleration of the system. So the picture shown in on the screen depicts what we call a vector diagram. And in order to more easily determine the net force, we're going to need exactly this condition here, this diagram, in order to make it simpler. Okay, even though it's shown there, I'm just going to represent a vector diagram where the object is simply a point at the center of the graph of the plane, and then given that we're gonna resolve all of the forces that are off the x-axis. In this case, all of them are off the x-axis and y-axis. So we're gonna resolve them into components, and then determine the sum of the forces on the y-axis to determine the x component of the net force. And afterwards, we are going to determine the vector sum of the forces on the y-axis, that is, the y component of the net force, and then determine the magnitude of the net force by means of showing the parallelogram rule, and also showing how we're gonna determine the angle, thus the direction that the net force is pointing relative to the x-axis. Okay, and then afterwards we're able to determine the net acceleration, given that we have the magnitude of the net force. All right, so here we go. So I'm just going to design to write again down the vector diagram where the object is just simply a point at the center of the plane. So here we have 100 newtons relative, I'm sorry, 100 newtons that is standing 45 degrees relative to the y-axis. But if it's 45 relative to the y-axis, it will also be 45 relative to the x-axis, given that the complement of 45 is also 45. Then F2 also making a 45-degree relative to the x-axis. So F2, 40 newtons. And then F3 making a 30-degree angle relative to the x-axis. All right. So now we're gonna resolve these each of these vectors into their x and y components. So resolving them into components means that we're gonna have their projections on the x-axis and y-axis. So then we have f1x just make it more clear for everyone to see. This is f1y. Then we're going to change color not to get you guys confused. So then we have f2x. We also have f2y. Last but not least, we have f3x a little bit more accurate is good. It's better. So f3y. Remember that when we show vectors, we should necessarily show the head, that is, the arrow at the tip of it that indicates where it's pointing to. All right, ladies and gentlemen. And also do not forget to label your vectors. Okay, so now given that we have a full vector diagram detailed, we can now calculate the pieces that will compose the calculation of the net force. Okay, so I'm just gonna copy and paste this vector diagram that we have just designed. To the next page, just a second. Just gonna copy and paste a copy of that to the next page in order so that we can more easily proceed with the calculations, especially of the x and y components. All right, so I know that the sum of the forces on the x-axis, that is the x component of the net force, will be composed of the vector sum of f1x plus f2x plus f3x. So pay attention, f1x, f2x, f3x. Okay, but we need to have the components, the x values of each of these vectors calculated properly, and this is what we're going to do. So in order to do so, we use trigonometry ratios, SOHCAHTOA. And remember that every time we resolve a vector into a component, we end up designing a right triangle such that this is the adjacent side relative to the 45-degree angle, and this, which is f1y, represents the opposite side of 45-degree angles. And so that said, we have f1x as being equal to 100 times cosine of 45. Why cosine? Because this is standing as an adjacent side to 45 degrees, okay? And 100 represents the hypotenuse. Remember that, just so you remember, if we did the conventional way, we would have cosine of 45 equals adjacent, which is f1, right? f1x over the hypotenuse, which is 100 newtons, right? 100 newtons. If we cross multiply, what happens? We end up with f1x equal to 100 times cosine of 45. But why am I doing this straight away like that? In order to save time and make it simpler, okay? But feel free to do this way on a test, not a big deal, not a problem, okay? As long as you understand and clearly show or communicate your reasoning, that's what matters to me. But definitely this information simply put, communicates well your reasoning. All right, FYI. So just gonna keep this pattern here for the other vector x components. I mean, so then we're gonna do the same for f2. So here is a right triangle such that 40 is the hypotenuse and f2x is the adjacent. So then we have 40 cosine of 45. Remember that that f2 is adjacent to 45. So adjacent resembles cosine. So hypotenuse times cosine gives you the adjacent. F3x is going to be now changing color. Let's make it, just make sure to show a proper right triangle. So 30 degree is standing adjacent to F3x. So we do the same thing as we did before. So adjacent resembles cosine, in this case cosine of 30. So let's calculate each one of them. All right, so 100 newtons times cosine, so I know that 100 times 0 0.707 should give us 70.7 newtons. Pay attention to one detail, because F1 is pointing opposite the x-axis. So then we should make sure to make this magnitude negative, because we want to indicate opposite direction and eventually plug in this information as a negative value in this vector sum above. Then we have 45. 45 is positive because it's pointing to the same direction as the x-axis. So that's going to be 40 times 0.707. That should give us, let's proceed with the calculation here. Let's get a calculator and do it. So 40 times 0.707. That should give us 28.28. So let's round it up to 1 decimal place. And last but not least, we have 60 times 0.866, which is cosine of 30. So the calculator gives us the following information. So it gives us 51.96. I'm just going to round it off to 52 newtons. All right. Now we have all of the data we need to calculate the x component of the net force. So the net force x should include negative 70.7, which is F1x, plus F2x, which is 28.3, plus 52. Okay, it is important to double check all of your calculations, because especially when we're on a test, we get to be nervous, we tend to blank out, we tend to mistype information in the calculator, especially when it comes to involving lots of calculations. It is important to double check each calculation that you proceeded. Okay, so this is what we're gonna have. So using a calculator here. And so we are left off with 9.6 newtons. So this is the information that we've got for the x component of the net force. Now, we need to calculate the y component of the net force, and this is going to include F1y plus F2y plus F3y. All right, so that said, we calculate F1y as being 100. So since we have used cosine of 45, we're going to use sine this time around. Even though they are the same, sine and cosine of 45 are the same because that indicates the angles of an isosceles right triangle, which is the case here. So this side is equal to that side. So we're pretty much going to have the same value as before. But pay attention to one thing, that f1y is pointing to the same direction as the y-axis. So we're going to have the value positive. Same thing is going to happen to f2y. So here we have 40 times sine of 45, which is the same value as f2x. Oops, I did something wrong. It's f2y. So then we have 28.3 newtons. Oh, let's see, it's also positive because it's pointing to the same direction as the y-axis. And f3y, and this time f3y is negative because it's pointing opposite the y-axis. So let's make it positive. So then we have 60. Now sine of 30. Okay, sine of 30 is different from cosine of 30 for sure. But I know that sine of 30 is 0.5. So that should give us negative 30 newtons. Okay. So with this information in mind, we can now set up a diagram with the vectors of the x and y components of the net force. So let's see here. We have the net as being 9.6 newtons. So, oops, I forgot something that I was almost forgetting. And we need to add up all of the some vector vector add the y components of the net force. I'm sorry. Just doing this in a hurry because this video is going to be a little bit long. So let's see here. So then we put 70.7 plus 28 minus 30. So this is going to give us, so just calculating here. So I've got 69 newtons positive. So we have a large y component for the net force in question, and a small one for the x-axis. So then we apply the parallelogram rule in order to graphically represent the net force. So this is the net force vector. So as you can see here, we form a right triangle. And so since this is this leg is equivalent to that, so we're gonna use 69 solely here, right? So we do Pythagorean theorem in order to calculate it. Ladies and gentlemen, it's important to pay attention that this video is a little bit longer than usual because I'm explaining the whole process and going over each of the concepts to make sure that you understand details that you could not unfortunately grasp during certain lessons of ours. So just take the chance to watch the video as many times as you like it, and make sure to uh, consolidate the information that was missing. Okay, so the net force is going to be calculated by means of using Pythagorean theorem. Okay, so this is what we're going to have. So we get 69.99. We can round it off to 70 newtons. So our net force is going to be 70 newtons. And it makes sense because the y component is much larger than the x component. So this impacts significantly in the value of the net force. And this is kind of close to it, as you can see, right? And now what do we do? Obviously, just to make sure that you understand, this vector diagram is not on, it's not shown to the scale, right? But one thing we should consider is to show the angle of the net force, which is the direction of the net force relative to the x-axis. Let's just show the x-axis here. And so for us to calculate this direction, we do inverse tangent of opposite, which is 69, to the opposite angle theta is 69, and adjacent is 9.6. So the direction is gonna be, let's calculate it. So this is gonna give us 1 degree, I got 0.99, which is approximately equivalent to 1 degree relative to the x-axis. I'll just put here relative to the x-axis. Okay. All right. So just going back, let's make sure that we answered all of the questions. So vector diagram, check. Determine the net force. So we have determined the magnitude of the net force, which is this. Let's just make sure to show that the net force is given by that. So equals F net. Okay. And the direction, which is 1 degree relative to the x-axis. And the system is clearly unbalanced since the net force is different from 0, which is 70. And the object is pointing to 1 degree relative to the x-axis. So it's the combination of the forces given are pointing to 1 degree relative to the x-axis at 70 newtons, and this is what happens, this is what occurs to the object, in this case this ring here. Now all that we have to do is to calculate the net acceleration of it, given that the mass is 15. So letter C. Oops, there's something here, clear the frame. All right, so here we go. So the letter C. All right, Gymboard is a little bit slow. I'm sorry. So letter C. So the mass given is 15 kilograms. The acceleration is what we're looking for. The net force is equivalent to 70. Given that Newton's second law equals net force equals mass times acceleration, we just plug in the information provided to find A. So if we isolate A by dividing this piece here by 15 on both sides, then we end up with 70 divided by 15, which is 4.7 meters per second, because that's going to give a repeating decimal, which is 4.6666. So rounding it off to 1 decimal place, this is what we got for the acceleration. And that's all about it. Thank you so much, folks. See you next opportunity. Bye-bye.